Hello friends, today we are going to start our revision for JEE on atomic structure. Well, to understand the behavior of an atom or an electron, you must know some of the basic concepts of a wave-like species. So, let's start. The first thing and foremost thing, some formulas that you must know is frequency. Or nu. We denote frequency by nu. Nu equals c upon lambda. C is the speed of wave. We take it as equal to the speed of light divided by wavelength of that wave. Wavelength of wave. Okay, and its energy. If any wave is in this particular state, its energy E is given by h nu. That is h into frequency, or this becomes equal to the hc upon lambda, where h is Planck's constant. Its magnitude equals 6.626 into 10 raised to the power minus 34 joule second. Okay. Now wave number is defined as, or h nu equals 1 upon lambda. Reciprocal of wavelength is wave number. Its SI unit is per meter. Now wave number of any line of hydrogen atom can be represented as a difference of two terms by the formula wave number equals RH 1 upon N1 square minus 1 upon N2 square. We will come to this formula later. RH is known as Rydberg's constant. And N2 and N1 are integers, where N2 is greater than N1 is greater than 0. Okay. Now, in case of hydrogen-like species means the species which have only one electron. For example, hydrogen-like species, their example is, suppose lithium 2+, or helium plus. They have got only one electron in their atom, so they can be termed as hydrogen-like species. They have got certain atomic number, and hence in these cases value of wave number is RH 1 upon N1 square minus 1 upon N2 square into Z square. Z is the atomic number of that species. Now, whenever these transitions take place, then if N1 equals 1, we call them to be taking place in Lyman series. Lyman series, it lies in ultraviolet region. If N1 equals 2, it is in Balmer series. It lies in visible region. And if N1 equals 3 or 4 or 5, we call them as Paschen, bracket, P-fund series, etc. series. And they lie in infrared region. The numerical value of RH is 109737 per centimeter. Okay, there came a scientist later known as Bohr, and he put forward some of his theories in which all orbitals were stable, in which he said that in Bohr model. That model is known as Bohr model, in which all orbitals are stable. All orbitals are stable and electrons would not be radiating energy. Like in Rutherford model, he said that electrons would be constantly radiating energy, but Bohr said that this is not so, because if electron constantly radiates energy, it will ultimately fall in the nucleus and then destroying the atom. This is because the angular momentum of an electron moving in a stable state is quantized. Bohr said that angular momentum of an electron moving in a stable state is quantized. Quantized means it is an integral multiple of h upon 2 pi. Therefore, MVR equals NH upon 2 pi, where n is principal quantum number. Principal quantum number. This theory is known as quantization of angular momentum. Quantization of angular momentum. So using this theory, Bohr came up with certain formulas for energy, velocity or radius of an hydrogen-like species. So using this, he came up with certain formulas, like we know that Coulombic force of attraction equals centripetal force, mv square by r, and we know MVR equals NH upon 2 pi. So from here we will get R equals NH upon 2 pi mv, or V equals NH upon 2 pi mr. So clubbing this and clubbing this, we get certain formulas for radius of a hydrogen-like species is n square h square upon 4 pi square k z m e square. So this is the formula for radius of an electron. For velocity of an electron, the formula was, if simplified further, velocity of an electron formula came 2.18 into 10 raised to the power 8 into z square upon n centimeter per second. If we put the value of r into this, and if we put the value of constants that we cannot change, we get the value of velocity as this: 2.18 into 10 raised to the power 8 z square upon n centimeter per second. And the value of r came out to be 0.529 into n square angstrom. Okay, so in any orbit with principal quantum number n, the value of radius came out to be 0.529 into n square angstrom. Or if the species is not hydrogen, if it is hydrogen-like, then we have to divide it by number of atomic numbers of that electron. So the value of r came out to be 0.529 n square by z angstrom. Value of v came out to be 2.18 into 10 raised to the power 8 z square upon n in centimeter per second. And the value of total energy came out to be 2 minus of 2 pi square k square e raised to the power 4 z square m upon n square h square. Or if we put the value of constants, we get the value of energy as minus 13.6 into z square upon n square electron volt, or minus 1312 upon n square into z square in kilojoule per mole. Okay. So from here we can say that R is directly proportional to n square upon z. V is directly proportional to z upon n, and E is directly proportional to z square upon n square. These proportionality terms are very much important while calculating or comparing the parameter of two or more species. Okay. So if we put forward all of these expressions into the expression of wave number, we get the value of RH, that is Rydberg constant, as 2 pi square m e raised to the power 4 into k square upon h cube into c. After calculating or after putting all the constants, we get the value of R as 109737 per centimeter. Okay. So after these theories were introduced, de Broglie came up with another theory. De Broglie came up. Its pronunciation is de Broglie. It's not de Broglie. Some people pronounce it as de Broglie. He came up with his own theory in which he proposed that an electron of energy E and momentum P could be defined by a matter wave whose wavelength and frequency are. Electron can be defined by a matter wave whose wavelength is h equals h upon P, and frequency is E upon h. Frequency is E upon h. So from here we get the value of wavelength equals h upon mv, and the value of energy as h nu. Okay. Let's now discuss about Heisenberg uncertainty principle. Heisenberg's uncertainty principle. Heisenberg uncertainty principle states that simultaneously, that is at the same time, and the accurate value of position and the accurate value of momentum cannot be determined. That is, neither the value of delta x nor the value of delta p will be 0, and he said that minimum value of the product of error in position and in momentum will be equal to h upon 4 pi. Said that this is the minimum value in the product of the error in position and momentum. Okay, so if we generalize it, then we get the value of delta x into delta p greater than or equal to h upon 4 pi. Now, quantum model. There is a theory known as quantum model in which principal quantum number n, azimuthal quantum number, is represented by L. Now, principal quantum number is n. In this, principal quantum number is n. Azimuthal quantum number is L, and it ranges from 0 to n minus 1. There is another quantum number known as magnetic quantum number. Magnetic quantum number, it's represented by m, and its value ranges from minus L to plus L. And there is another quantum number known as spin quantum number. Spin quantum number, as it represents the spin of an electron, and its value is plus half or minus half, to represent the spin in two directions. So the total number of radial nodes, we know that the node is the place where the probability of finding the electron is 0. If we consider psi, node is a place where psi square equals 0, that is probability of finding the electron is 0. If you consider psi, that is a wave function of an electron, then psi represents all the characteristics of that particular electron. So node is the place where the presence of electron is 0 in all respects. Okay. So the total number of radial nodes in any atom with principal quantum number L and azimuthal quantum number L and principal quantum number N for its electrons, then the total number of radial nodes equals N minus L minus 1, where N is the principal quantum number of that particular electron, L is the azimuthal quantum number of that particular electron. Okay, so total number of angular nodes equals L. This is the total number of angular nodes. Therefore, total number of nodes equals N minus L minus 1 plus L equals N minus 1. This is the total number of nodes for a particular electron in any hydrogen-like species, or in any atom. The total number of nodes for a particular electron is given by N minus 1. So let's discuss some of the problems. The first question says that an electron in a Bohr orbit of hydrogen atom in quantum level N2 has an angular momentum of 4.276 into 10 raised to the power minus 34 kilogram meter square per second. If this electron drops from this level to the next lower level, find the wavelength of this spectral line. So first, this question is asking that find the principal quantum number in which that particular electron is residing, and then when that particular electron comes down from that level to the lower level, what will be the wavelength of that particular spectral line. So to start with the solution, first we need to find out the value of principal quantum number in which the electron is there. Okay, so since we know from Bohr model that MVR equals NH upon 2 pi, N is the value of principal quantum number. We are given with the value of angular momentum. It is 4.276 into 10 raised to the power minus 34 equals N into 6.626 into 10 raised to the power minus 34 upon 2 pi. So from here, value of N comes out to be 4. This is our principal quantum number in which the electron is residing is 4. Since it is given that it is N2, hence we will denote it by N2. So N2 equals 4. Now it is coming to the next lower level. Next lower level means next lower level, that is N1 equals 3. So we know that wave number, or 1 upon lambda, equals RH 1 upon N1 square minus 1 upon N2 square. So if we substitute all the values, we get the value of 1 upon lambda equals 1.9, it's 109,679 into 1 upon 9, that is 3 square, minus 1 upon and 2 square, that is 4 square, or 1 upon 16. The value of RH was given in the question. It was 109,679. Okay. Well, from here the value of lambda comes out to be 1.8756 into 10 raised to the power minus 4 per centimeter, or lambda equals 18756 angstrom. This was what we were supposed to find. All the value of constants will be given to you in the question. So in this case, value of RH will also be given to you in the question whenever it will be asked. So you don't need to remember some constant terms, although it is highly recommended that please do so. Anyways, so going on to the next question. The question says that circumference of the first Bohr orbit in H atom is 3.322 into 10 raised to the power minus 10 meter. What is the velocity of electron in this orbit? Okay, so if we consider the Bohr model, we know that MVR equals NH upon 2 pi. And if we rearrange it, we get the value of V equals NH upon 2 pi mR. We can also write it as V equals NH upon 2 pi R into M. So here if we substitute all the values, we are given with N is 1, into H is 6.626 into 10 raised to the power minus 34, divided by value of circumference. 2 pi r is nothing but the circumference of any particular circle with radius r. So here the value of circumference is given to be 3.322 into 10 raised to the power minus 10. And mass, we know the value of mass as 9.1 into 10 raised to the power minus 31 in kilograms. So if we simplify it further, we get the value of velocity as 2.19 into 10 raised to the power 6 meter per second. So just remember this technique, how to rearrange some of the formulas to get the required expression. So moving on to the next question, it is given that the Schrodinger wave equation for hydrogen atoms is psi 2s equals 1 upon 4 under root 2 pi, 1 upon a naught to the power 3 by 2, 2 minus r upon a naught e raised to the power minus r upon a, where a naught is Bohr radius. Let the radial node in 2s be at r, then find r in terms of a naught. Well, this problem might seem a little bit of complicated because the value of Schrodinger wave equation is given, but here we just need to understand some of the few terms or some of the few concepts that we discussed during the discussion of concepts, that at node value of psi square is 0. Okay. Now if we apply this concept here, if we find the value of psi square that is given to us, then this problem will be quite easy. Just only this concept needed to be applied here. Okay, so looking at the problem, just make sure that you do not get scared by the way the problem is written. You just go through your basics. At node we know that psi square equals 0. And since psi 2s is given, we have to find the value of radial node in 2s orbit. So in 2s state, psi square 2s will be 0. Okay. Now psi 2s is 1 upon 4 under root 2 pi 1 upon a naught to the power 3 by 2, 2 minus r upon a naught e raised to the power minus r upon a. So if we square it, then psi square 2s is 1 upon 16 into 2 pi 1 upon E naught to the power 3, 2 minus R upon E naught square into e raised to the power minus 2R upon A naught. Okay. This quantity should be 0 so that the electron so that the electron is at the radial node, or the position that we are considering is the radial node. So there should not be any electron. Psi square 2s should be equal to 0. We know that 1 upon 16 into 2 pi is a constant term, so this cannot be 0. 1 upon A naught, since A naught is not infinity, so this can also not be 0. E raised to the power minus 2R upon A naught, so no matter what is the value of R, this term cannot be 0, and hence we are left with only this term which should be 0 to make this whole expression 0. So 2 minus R upon A naught whole square, it should be 0. So from here we get 2 minus R upon A naught equals 0. So 2 equals R upon A naught, or from here we get the value of R as 2 A naught. So at the distance R equals to A naught, we will have the radial node in this hydrogen atom, whatever we are given. So at R equals to A naught, we will have a radial node in this hydrogen atom. Okay, so this easy problem appeared in IIT JEE 2004. Okay, so let's discuss another problem. The problem says a baseball having mass 100 gram moves with velocity 100 meter per second. Find out value of wavelength of baseball. If error in momentum is 1%, find minimum error in its position. So this problem is based on Heisenberg uncertainty principle, and we will have to club two concepts in order to solve this problem. The first concept is that of de Broglie wavelength. So let's discuss de Broglie wavelength. It says h upon mv, lambda equals h upon mv. So from here the lambda equals 6.626 into 10 raised to the power minus 34 divided by 100 into 10 raised to the power minus 3. Since the mass of baseball is 100 grams, so converting it into kilogram, 100 into 10 raised to the power minus 3 into 100 equals 6.626 into 10 raised to the power minus 34, into 10 raised to the power minus 35 into 10 raised to the power minus 35 meter. So we get the value of wavelength as 6.626 into 10 raised to the power minus 35 meter. Okay, so P, the value of value of momentum is 100, that is velocity is 100 meter per second into mass, mass equals 100 upon 1000. So the value of momentum is 10 kilogram meter per second. Okay. Now we are given with 1% error in momentum. Therefore, delta P equals 1% into 10, that is the value of momentum, equals 0.1 kilogram meter per second, and hence delta x will be, the minimum error in position will be h upon 4 pi into delta P. Okay, because we know that according to Heisenberg principle, delta x into delta P equals h upon 4 pi. Its minimum value is h upon 4 pi. So from here the value of delta x comes out to be, h is 6.626 into 10 raised to the power minus 34 upon 4 pi into 0.1. So if we simplify it, we will get the value of uncertainty in position as 5.27 into 10 raised to the power minus 34 meters. Now since this value is negligible, we cannot observe this value through our naked eye, hence Heisenberg uncertainty principle generally do not apply to macroscopic objects. So this problem also appeared in IIT JEE. It appeared in IIT JEE in 2004. Okay, so let's discuss another problem. The problem says that positronium consists of an electron and a positron which has the same mass and opposite charge. That is, a positron is a positive species with the mass of that of an electron. So positronium consists of an electron and a positron orbiting around their common center of mass. The spectrum is therefore expected to be hydrogen-like, the difference arising from the mass differences. Calculate the wave number of the first three lines of Bohr series of positronium. Okay, Bohr series lies in visible region as we had already discussed, and in this case Bohr series has got the value of N2 as 2. So the value of N1 as 2. So the value of smaller quantum number is 2. Okay, so the problem says that positronium consists of an electron and a positron. So positronium consists of an electron and a positron. Suppose this is an electron, this is a positron. Okay, orbiting around their common center of mass. There is some center of mass, they are orbiting around it. The spectrum, now if we are taking the spectrum, obviously the spectrum is not going to be that of an electron, and hence we cannot apply this formula as nu bar equals RH 1 upon N1 square minus 1 upon N2 square. We cannot apply this formula because in this case the value of R, that is Rydberg constant, is given for hydrogen, that is species with one electron. And since this is not that case, hence the value of R is not going to be same. So we will go back, and since we know that R equals 2 pi square m e raised to the power 4 k square upon h cube c, we are going to apply this. Now here also we cannot apply 2m. Okay, because this is not a point species, so we cannot apply 2m. Mass is obviously this system mass has got 2m, but we cannot apply here 2m. We are going to apply, instead of mass, we are going to use mu, that is reduced mass. So we know that reduced mass equals m1 m2 upon m1 plus m2. In this case m1 equals m2 equals m, that is the mass of electron, and hence therefore value of reduced mass comes out to be m by 2. So the value of R in this case is 2 pi square mu a raised to the power 4 k square upon h cube into c, or substituting the value of mu, we get 2 pi square m e raised to the power 4 k square upon 2 h cube into c, or it is RH by 2. So the new value of Rydberg's constant is RH by 2. So from here the value of R is 54868.5 per centimeter. Okay, so the only thing that you should keep in mind that here the value of R is not going to be that we use generally. Okay, so now the problem has been simplified. Now the first line of Bohr series, first line will be given by nu bar equals 54868.5. N1 will be obviously 2, so 1 upon 4 minus, for first line N2 equals 3, so it will be 1 upon 9. So simplify it, we get the value of 7620.6 per centimeter. So the value of wave number is 7620.6 per centimeter. Similarly, For second line, nu bar will be 54868.5 1 upon 4 minus 1 upon 16 or equals 10288 per centimeter. And for third line, nu bar equals 54868.5 1 upon 4 minus 1 upon 25 equals 11522 per centimeter. So these were the answers that we were supposed to get. So remember, this is a tricky question in which we cannot use RH to be as the same of the conventional value. Moreover, the value of R will also not be equal to 2 pi square into 2m. That is, if we take the value of m as 2m. So here we are supposed to calculate first the reduced mass and then substitute it in the expression of R, then get the new value of R, and now apply that formula to get the first, second and third line respectively. Well, now let's consider another question. The question says that the circumference of the second Bohr orbit of electron in hydrogen atom is 600 nanometer. So first, while looking at this problem, the first thing that we should note is n equals 2. The circumference of second Bohr orbit of hydrogen atom 600 nanometers. So 2 pi r equals 600 nanometer. So these are the two things that we have got from the first line. Calculate the potential difference to which the electron has to be subjected so that the electron stops. What should be the electron? That particular electron has got some of the energy, kinetic energy. So what should be the value of potential difference so that if we apply it, then the electron acquires that much of energy that it stops, or it loses that much of energy. Well, so that the electron stops, the electron has had the de Broglie wavelength corresponding to this wavelength. So in both of the cases, that is, if we use Bohr model and de Broglie model, they both will get the same number of wavelength. Therefore, in this case, in the last reading the last line, we can club Bohr model and de Broglie model together. So now clubbing these two models together, we get the value of MVR equals NH upon 2 pi. Okay, so from here, the value of MV is, we know that this is the Bohr model. Okay, this is the Bohr model, and H lambda equals H upon MV. This is the de Broglie model. Okay, so if we club both of them together, we get the value of 2 pi r equals n lambda, or from here the value of lambda as 2 pi r upon n. Since the value of 2 pi r is given 600 nanometer and the value of n is 2, so the value of lambda is 300 nanometer. Okay, so we have got the value of lambda. Now, since lambda equals h upon mv, so from here the value of mv is, or the value of v is h upon m lambda, or if we square both sides, then v square will be h square upon m square lambda square. Okay, so we have got the value of v square. Now, if V naught is the voltage, then EV naught should be equal to half mv square. Okay, or this implies that this implies that V naught equals half m upon E into h square upon m square lambda square. Simplifying it, we get the value of half h square upon m lambda square into E. So we know the value of h, we know the value of lambda now, we know the value of E, we know the value of m. So V naught equals 6.626 into 10 raised to the power minus 34 upon 2 into 9.1 into 10 raised to the power minus 31 kilogram. So this is in joule second into 300 into 10 raised to the power minus 9 meter of square into E, that is 1.6 into 10 raised to the power minus 19 coulomb. Okay. So using the scientific calculator, you can use the scientific calculator to get to the value of V naught. The value of V naught will be, in this case, if we simplify it, V naught equals 6.626 of whole square into 10 raised to the power minus 68 divided by 2 into 9.1 into 10 raised to the power minus 31 into 300 square into 10 raised to the power minus 18 into 1.6 into 10 raised to the power minus 19. So the value of V naught is 6.626 squared into 10 raised to the power minus 68 divided by 18.2 into 9, or we are taking out 2 zeros from here, into 1.6 into 10 raised to the power minus 31 into 10 raised to the power minus 14 into 10 raised to the power minus 19. Okay, so from here the value of V naught is 6.626 squared upon 18.2 into 9 into 1.6 to 10 raised to the power minus 4. The unit is in volt. Okay, so this is left to you. Just solve it. We will come across this. We will come with the exact value a little bit later. Okay, the next question says the work function of metallic rubidium is 2.09 electron volt. Calculate the kinetic energy and the speed of electrons ejected by light of wavelength 650 nanometer. Okay, so here we are going to use the concept of photoelectric effect, which says that if any metal is given to you and you want to eject an electron out of it, then you will have to irradiate it with a photon of certain frequency, and the frequency should be such that the energy of that photon should exceed the threshold energy that is of that particular metal. Okay, so we know that from here E of photon equals phi, that is the threshold frequency, plus Ek, that is kinetic energy of that particular electron. Okay, so, and we also know that energy of photon is h into nu. Fine. So therefore phi plus Ek should be equal to h nu, or from here the value of Ek, that is kinetic energy, should be equal to h nu minus phi. We are given the value of nu that in the form of wavelength. So wavelength is, since wavelength equals c upon lambda, therefore Ek equals hc upon lambda minus phi. So now we have got the value of lambda, we know the value of c, we know the value of h, we know the value of phi. Okay, so we can calculate the kinetic energy. So now if we put the value of lambda as 650 nanometer, the value of Ek is 6.626 into 10 raised to the power minus 34 into 2.998 into 10 raised to the power 8 divided by 650 into 10 raised to the power minus 9 minus 2.09 into 1.6 into 10 raised to the power minus 19. Okay, so the value of phi is given as 2.09 electron volts, so we have to convert it into joules. So converting it into joules, we will have to multiply it with 1.6 into 10 raised to the power minus 19. So if we simplify it, the value of Ek comes out to be minus 2.88 into 10 raised to the power minus 20 joule. But remember, since the value of kinetic energy cannot be negative, therefore we can say that there is no kinetic energy, because it cannot be zero. And hence the photon does not have enough energy to dislodge the electron. Therefore, photon does not have enough energy to dislodge the electron. Now if we increase the energy of photon, say that we have increased the energy of photon to another value of lambda, if we take it as 195 nanometer, then the value of Ek will be 6.626 into 10 raised to the power minus 34 into 2.998 into 10 raised to the power 8 divided by 195 into 10 raised to the power minus 9 minus 2.09 into 10 raised to the power minus 19 into 1.6. So here we'll get the value of velocity, or the value of Ek as 6.84 into 10 raised to the power minus 19 joules. So here the electron has been ejected because it has got some kinetic energy, and now the value of velocity, since this is equal to half mv square, since Ek equals half mv square, so from here we get the value of velocity as 1.23 into 10 raised to the power 6 meter per second. Okay, so just remember that in the first case, since kinetic energy has come out to be negative, so there is no kinetic energy, hence there is no velocity. It is not that you come up with the value of kinetic energy as negative and then you calculate the value of velocity by taking its magnitude. Please do not do that. Okay, so let's discuss another question. The question says, it has got three parts. In the first part it says that calculate velocity of electron in first orbit of hydrogen atom. Okay, so if we apply here Bohr model, we know that mvr equals nh upon 2 pi. So from here we get the value of V as nh upon 2 pi m into r. The value of r is given to us, or we already know that 0.529 angstrom is the value of r. So, and n equals 1, we know the value of m. So from here, if we apply all these constants, the value of V comes out to be 2.18 into 10 raised to the power 6 meter per second. Okay, so the first part has been solved. Very easy question. The second part says that find de Broglie wavelength of the electron in first Bohr orbit. Okay, now the value of V, we know the value of V. So, and also by de Broglie hypothesis, we know that lambda equals h upon mv. So from here, lambda will be 6.626 into 10 raised to the power minus 34. Into 10 raised to the power minus 34, dividing by 9.1 into 10 raised to the power minus 31 into 2.18 into 10 raised to the power 6, because we know the value of V from here. It is 2.18 into 10 raised to the power 6. So from here, if we simplify it, we get the value of lambda as 3.3 into 10 raised to the power minus 9 meter, or it is 0.33. It is 0.33 into 10 raised to the power minus 9 meter, or it is lambda equals 3.3 angstrom. Okay, so second part has also been solved. The third part and the final part of the question, it says that find the orbital angular momentum of 2p orbital in terms of h upon 2 pi units. So if we solve the third part, we know that for 2p value of azimuthal quantum number L equals 1. Okay, and therefore orbital angular momentum, since orbital angular momentum equals under root L into L plus 1 into h upon 2 pi. Now substituting the value of L here, we get the value of orbital angular momentum as under root 1 into 2 h upon 2 pi. Here we get the value as root 2 into h upon 2 pi. Okay, so we have solved this question. This was very easy problem which appeared in IIT JEE 2005. Okay, now so coming back to the problem that we left to you to solve, the value of potential comes out to be 1.67 into 10 raised to the power minus 5 volt. So this may not seem a big number in terms of magnitude for potential difference, but if we take care of the microscopic levels of electrons, then it is certainly a very big number. So the electron must be subjected to the potential difference of 1.67 volt, must be subjected to the potential difference 1.67 into 10 raised to the power minus 5 volt in order to be at the stationary state for that electron. Well, with these problems we have come to the end of our discussion of revision on atomic structure. So that's all for this video. We'll see you in the next video.